once we can start to amalgamate these trees into one set of rules, or aggregate multiple trees, each one is a different randomized view of the data. And by running it through that, we get a better, more generalized approach, more generalized model. So we don't get overfitting. So any questions on that so far? Okay, so there's a few other things we need to consider. And this is where we get into gardening and arboriculture. So first of all, a tree can be very complicated. You could have, theoretically, as many branches in the tree as you have individuals. So this is a branch for this individual, this is a branch for this individual, and those branches get very complicated. So we can prune the tree to make it more generalized. We effectively take branches out and put them back into one amalgamated group, which may not be perfect, but it will do reasonably well. It will be more generalizable. So we can start taking out branches. We can effectively look at consensus across the random forest. We can merge trees into kind of one amalgamated tree, and we can have partial decisions on branches as well. I'm not going to go too much into that because that gets a bit more complicated. Suffice it to say, random forests are a pretty good classifier. They work quite well. They can work well for relatively high dimensional data, and we've seen sort of similar performances in random forests to neural networks. It's an alternative tool. So that's the end of that lecture on the introduction to machine learning. I think we don't know if Arup needs to give his extra lecture. Now, I don't know, maybe he's somewhere else. I'm just going to see what we've got next. I think it's... Okay, I'll start getting into this. This is kind of quite contiguous until Arup comes back. So, I've got Wi-Fi, yes. So these are, what I've tried to focus on here is very much a no-code approach to using machine learning for visualization, for undertaking analysis. Running to code in R or Python or Java is quite a different undertaking, and it's probably best learnt by doing, and could take, those sort of coding courses take 6 months to run. But I would recommend, if you want to seriously get into coding seriously get into machine learning, ultimately using those methods, because they will empower you to automate processes. They will empower you to try out experiments. The methods I'm going to show you, certainly Weka is perfectly acceptable and usable. People publish papers where they've done work in Weka as a workflow. And you can do a whole load of stuff there. You can do deep learning. Weka's Java-based, so you've got all sorts of modules around deep learning which you can use. You can do convolutional neural networks. You can do recurrent neural networks. It's very powerful. So you won't be limited by that. Oops. So the first, let's see if we can. Let me link to that. Okay. Seeing if I can get onto the internet now. Don't have an internet connection. That's live at the minute, it seems to have gone down. So the first, I can talk about it, but I'll show you in a bit. So the first piece of no-code software I use is one called Orange. If you Google Orange data mining, then what it will give you is a load of instructional videos on how to use it, but it has a workbench type format. So you basically drag widgets onto a workbench, and those widgets do things like load files, transform the files numerically, apply an algorithm, take the results out to a spreadsheet, allow you to plot a graph, and it creates a workflow which you can do various things. What it's really quite good for is learning, but it also has some other useful tools. So for example, it's got a spectral element, so you can do spectral aligning in it. So if you're using mass spec and your instrument doesn't have onboard spectral alignment or spectral cleanup or smoothing, averaging, all that stuff, you can do that in Orange as well. It also does things called t-SNE plots, which is very useful for visualizing data, where normally most people use principal components analysis on their spectral profiles to see if they've got outliers or structures. What a t-SNE plot does, the limitation of principal components analysis is that you might have one component that only explains 5%, and the second component only explains 3% of your variation in your data. The problem with that is you've only then got 8% coverage of what's happening to the rest of the noise in the data. So you're only using the tiny fraction. What a t-SNE plot does is, in effect, takes multiple components and using effectively a kind of form of multi-dimensional scaling, it allows you to put a 2D plot with up to 20, 30 principal components on it and position all your points in a 2D space. So you can collapse all those components down into one graph, which is very useful, because if you want to find out if there's batch effects or if there's noise or outliers, then you can do that. Do you know what a batch effect is? Okay, I think I'll talk about this later, but I'll quickly cover some of it now. So a batch effect is, let's say you run your first set of samples on the mass spec, and you get your results, then you go away on holiday, the instrument's recalibrated, and you run your mass spec on a second set of dates. There will be implicit variation caused by that change in calibration between those two populations. So normally you can only work on one or the other of those data sets. What batch correction does is effectively allows you to overcome that batch effect and normalize your points back so that they're all in the same range. So that's a useful technique. I'll talk a bit more about it in a subsequent lecture. But you can do you can use the t-SNE plot to check for batch effects, and then you can use something called combat to batch correct. That's a useful set of tools. Right, okay, let's try and get a new Google window. Yep, there's nothing happening here.
I have internet connection, you may use.
Is it high? Sorry?
Well, it's not working.
Okay. Just down here. You have a hotspot, and there's a hotspot there. What's your hotspot? So G73.
Refresh the answer.
Yeah. Strange.
It's no sign.
I think you've hidden your device. I'm not sure if that might work.
No such sign.
Try again. Compatible with Mac OS, and it's compatible with Unix, if any of you got a Unix machine. Thank you. So, it's getting there, I think. That's taking me to a Udemy course. That's not what I want. That's why. There we go. So this is the Orange webpage, orangedataMining.com. If I go to, this is just the page for it, it's about visual programming. Let's see. Right, so if I look at videos, there's a whole YouTube channel for this so there we go. So we've got a welcome.
The first thing you will see is a welcome screen. From here, you can start a new data analysis workflow, Science. Hello and welcome to Orange Tutorials.
So this gives you tutorials, it tells you how to work through various methods, it tells you the basis of the methods.
You have probably already downloaded and installed Orange. If not,
and you can see it's got getting started with, it tells you about neural networks, it tells you about visualization, it tells you about a whole range of different tools. I'll close that down, and I've got Orange running here. Everything seems to be on the go slow today. Here we go. So what I've got, the first thing is the splash page. I'll create a new workbook. I'm just going to skip that. So what you've got, for example, here is I've got a widget, and that says CSV file import. So that's pretty much the standard form of these sorts of data sets. So it's a comma separated value, easily read in Excel, but also many text type formats like that with CSV as a standard. So what I can do is if I double click on that, I can select a see if it's desktop. I can select a data file. I just want to Books documents. There we go. Is that it? Yep. Data for course. So I've got a data set which is just a toy data set which will show roughly how it works. What I've got is a set of variables, TNF alpha, PI3K, IgG, ER, MMP9. And then I've got a class, this is a classification problem, which says disease 1 or disease 0. So 1 if it's a disease case, 0 if it's a control. So that loads in that data set as a CSV. You can get an update widgets which also allow you to load in from Excel or from other sources as well. So I've loaded that data in. Now what I might want to find out is how to do that. I can click on help. Hopefully help is working. So it tells me all about how to do that and what it means as well. So I can figure out what I need to do to get the file into Orange. What I then do is I want to be able to select columns because I want to tell it what's my input and what's my output. What am I trying to predict? What am I using to predict? So that just gives me a selection tool, but what I need to do is link my data to that selection. So you can see how there's a dotted line here and it changes, becomes a different shade when I'm over it. If I move my cursor over that, hold the mouse down and drag, I create a pipe which sends the data from the import through to the select columns. So now you can see it's detected automatically for me. I've got my input variables and I've got my thing I'm predicting, my dependent variable. These are independent variables, this is a dependent variable. So that's the next bit I need to fix or sort out. So now I have a set of data and I have a selection, a variable selection piece. Right, so what else can I do? Well, one thing which might be useful is a t-SNE plot. So if I click on help for this, it tells me all about a t-SNE plot. It's two-dimensional data projection. So it's t-distributed stochastic neighbor embedding. It tells me all about that, how I can do various things with it, and how I can pre-process data, and so on. So it's a useful instruction how to use that, and that's a technique that's quite widely used. So I'm going to take the data into that. You can see it's running. Now if I click this, you can see I've got a two-dimensional plot of my cases. It has highlighted which ones are healthy, which ones are disease. This one's using 3 principal components. It's only 5 variables, 6 variables in the data, so it's not going to use many more than that. But I can increase that to see if it makes a difference. Let's take it up to 4. I've got distance metrics. I can exaggerate, and you can see by using more principal components it creates the shape a bit more. I can see potential outliers, I can see clusters, I can see groups of individuals who are behaving the same way. Some things I can switch on and off, like the global structure, that hasn't made much difference there. I can choose to normalize the data or not. That can have a big impact. Is that completed? If it has, it's not very good. Probably does need normalizing then. And then what I can do to visualize this is I can set them as a different color, set them as a different shape, and I can show color regions. So there's not really much of a color region, although the blue areas you can see are shaded blue, and there's kind of an edge to our disease cases around here and a bit around here. So we can use it to get an understanding of what's happening in our data. If I'm using this for gene expression array data, what I usually do is pull housekeeping genes off the array, usually 15 housekeeping genes, and it allows me to run this on housekeeping genes, which means they should all be the same. They should be relatively invariant across a population. So if I get big differences in those, and I can see obvious groupings, then there's a clear batch effect going on. I don't want to do a t-SNE plot on every single transcript, but I do want to, say, pick a number of housekeeping genes to see if there's that structure in there. That's a useful tool. If I want to export this, I can put it to a note by moving the cursor over down here. I can also save the image as a graphic, PNG or JPEG or PDF. So that's the first thing I can do. I'll close that down. What I can also do is I can use some unsupervised approaches, so I can do clustering. So I can see whether there is a particular cluster in the data. So that's hierarchical clustering. I'm not going to go into that too much, but we can use it to look at groups. And then I can start to get into machine learning. So the widgets for that are model. And you can see I've got decision trees, I've got random forests, I've got support vector machines, logistic regression, neural networks, Bayes. So I've got a whole set of different machine learning tools that I can use. I'll just maximize that. So what I'm going to do is I'm going to create a neural network. So what I need to do is take the data from my select columns, drag that into the neural network, and then double click on that. You can see I've got various functions. I've got a logistic, identity, TANH, ReLU. I can choose one of those. I'm going to take a logistic for now. So I'll take TANH for change. And then I've got a solver. These are kind of extensions or further developments around the entropy compared to the gradient descent method I showed before. I'm not going to go into those, you can look those up yourself. And then I can choose the number of neurons I have in the hidden layer. So if you remember, I said if it's a really big neural network, it can overfit. And in this, I've got 100 neurons in a single layer. If I typed into there 100, 100, 100, I would have 3 hidden layers of 100 neurons. So that would be a really big network. So I'm just going to take that down to, I'll take it to 5. I can choose the amount of regularization. So regularization is a technique which stops the weights going too wildly away when it's training. It just prunes the network a little bit and prevents overfitting. So once I've got that, then what I'm going to do is test my neural network. And I take a line from the neural network, which is the predictions, into this widget. And I take a line from this, which is the ground truth. And what it does is I can now see that my neural network has various parameters. This is the area under a rock curve. So an area under a rock curve is basically the 1 minus sensitivity against specificity, if I remember rightly. So I'm just going off the top of my head. But basically, the area under that curve, the closer it is to 1, the better the classifier is. And anything with an AUC of 0.8 or more, it means it's explaining 80% of the variation in the population, regardless of the threshold at which you choose. So this is not too bad, 0.766, but it probably could be better. Yep. So it's explaining about 77% of the cases. Now I can also, I'll do a random forest as well. And you know how I said about kind of using hyperparameter tuning? Well, I can start to build multiple models into this, and for my data I can try them all out and see which ones do well, which ones do less well, and cross-compare them side by side. So now, if you look, I've redone that, and my random forest has done less well than the neural network. I'm going to add in a support vector machine, and take that one to that one. So the SVM now has done much better. That's got an AUC of 7.795. So for this data, it appears that an SVM is a good solution. Now, once I've got that, I can do other things. So if I can do a rock analysis, so if you remember I said what a rock curve was. So it's basically sensitivity against 1 minus specificity, and the curve goes, should ideally go up to 1 and then across if it's a perfect classifier. But what this does is looks at different thresholds, decision thresholds. So the algorithm makes a prediction of a value between 0 and 1. And that's the probability that it's a disease, in this case a disease class. So if the value is 0.01, and it's a healthy class, that's very accurate, because that state is a 0, it's made a prediction of 0.01, it's just 10% error. If it makes a prediction of 0.01 and it's a disease case, then it's getting it badly wrong. There it's got 90% error. If it makes a prediction of 0.5, that's the decision threshold. So, it's more, if it's over 0.5, it's more likely to be like disease than it is healthy. So by using that and changing that threshold, we create this ROC curve, or the system creates this ROC curve. And you can see this one doesn't give a key, which is a bit awkward. Oh, it does, yeah. So this one is the SVM, and that's doing much better across a lot of the curve, apart from the neural network does better in this bit. So we've got that analysis of our model, of our classifier. We can also do things like take out, let's go to data table. We can take out the predictions. So what we've got here is we've got our ground truth, and for this first case, the neural network predicted it as 1, which is correct, and the other two predicted it as 0. So the probability of a 1 here was 0.7, so it's got a higher probability of being a disease. The probability of a 1 for the random forest was 0.38, so you can see it's got it wrong, and the probability of the SVM of 1 is 0.41. So it's given me probabilities for each individual in the population, and it's got the variables as well. So I can slice into all my models and see how they work for each individual in the population. So something else we have in here, I think it's, it hasn't got so many. So if I click on options and add-ons, there's a whole list of extra packages which I can use here. And that gives us a lot more functionality, a lot more power, what we do. So a few of these that are important. So bioinformatics, that gives us access to a whole load of biomedical data sets, like from GEOD, so transcription, so expression array data and RNA-seq data. Geo is a geographical package. Image analytics allows us to look at images and do thresholding and put filters in for images. Prototypes allows us to build functional prototypes of models, where we can build a model and put it out to a package. Spectroscopy, I'll open that one. This is specifically for analysing spectrograms, like mass spectrograms. So it's just taking a little while. These are not big things. Right, so if I restart Orange now, so if I go to spectrograms, oops, what's that come to? Spectroscopy, here we go. So I've got things like spectra, so I can load spectra in. That's a data table. I've got hyperspectra. I've got interpolate, so that allows me to do interpolation of missing values. I can pre-process spectra by smoothing. I can integrate spectra. I can do peak fitting. I can create tile files. And I can do calculate signal-to-noise ratios. I can do partial least squared analysis of the spectral profiles as well. So it does quite a lot. A line stack does aligning of spectral peaks as well. So we can align spectra with this too. So that might be useful as well. What I would say is orange is a good starting point, it's a good way to learn, but it doesn't have so much functionality. You're limited in the hyperparameter tuning. You're limited by how you can do that. You can't automate hyperparameter tuning. You're limited by a number of algorithms. Whereas Weka, which I'll show later, is a complete open source solution where people are adding new algorithms, new techniques all the time. So it's a kind of a community-based solution. Well, Orange is a community, but it doesn't have anywhere near as many features. So I'll cover that in the next lecture, and then we'll start looking through some other techniques as well. Any questions?
So like you have given the input of one CSV file.
Yeah.
So if we have like different CSV files for the same data, like different study with different parameters, so will it like get into same training set?
If you've got different parameter sets, then it's going to be difficult to merge those into one file which is contiguous, unless there's overlapping features. What I would tend to do with that is I'd run the two in parallel, and then look at what was found to be important in those two separate parts.
Then we can do it separately.
Yeah, yeah. You can load, with Orange, I think you can load some quite big files. With Weka, you can load big files as well. You may have to, there's some tweaks that you can use to increase the memory allocation of Java as well. But you can also tweak Weka to use GPUs as well. So, any other questions? Yeah. Yes, you can. Yeah, so there are so in Visualize, I think it is. Yeah, in Visualize you've got a heat map widget. So you can take, let's see if we take that value out of there, whether that will do anything. Yeah, it's not been scaled properly. Does that need to scale that one down a bit? Yeah, the values are not evenly distributed, but if they're on the same range, then you can select heat map for those variables. You can probably point at particular variables and change the range for each one of those as well. But yeah. Any other questions? Somebody else put their hand up, I think. Yeah.
So how's the threshold value decided to classify as diseased or healthy?
So it's normally set at 0.5, because that, if you have a continuous distribution between 0 being healthy, 1 being disease, it's halfway along that distribution. Now, so let's say I make a prediction. My first individual has a value of 0.4 and they're 0. Yep. That's fine, that's correct. My second individual has a value of 0.48 and they're a disease case. My third individual has a value of 0.6 and they're a disease case, that's correct. What some people do is they move the threshold to improve the accuracy either for the positive or for the negative cases. The reason they do that is, let's say you have a clinical study. You want to be more accurate at diagnosing people who have cancer and getting that right than you do at diagnosing people who haven't got cancer. At the end of the day, if you've got somebody who hasn't got cancer and you get it wrong, so you have somebody that the algorithm says that they've got cancer and you get it wrong, that's not such a bad thing as somebody who you are saying is healthy but they have cancer. So you change the threshold to give a better classifier in one particular direction. But yes, the 0.5 is normally the standard cut point.
So how we will do if you have normal disease rate along with population and gender and other variables?
Yeah, they're all variables. You can use them as long as you effectively put them into the algorithm can scale them. One of the things about machine learning is you don't have to have every single input as a continuous value. You can have it as a class as well. So you could have gender being, let's say, 1, 0. So you can use that as a variable, put it into your model. Yeah. So it's more flexible than conventional modelling. So. Okay, any other questions? As I say, the best way to learn what orange and weka and things like that is to go and play, get some data. There's a lot of data sets in the package which, in the tutorials will point to. So have a play with their data and try things out. The guys at IITB that have run this course with them a number of times, and they use orange quite a lot. Even though it's a relatively simple solution, they do use orange quite a bit. So, okay. I think it's probably a good time to break for lunch now. I think we have lunch. So I've just taken you through a little bit of